I'm Lawrence Weschler. I'm the director of the New York Institute for the Humanities at NYU, and I'm visiting here on various accounts, but especially, I think, to introduce Margaret Wertheim, who I'm sure you're going to enjoy this evening. Some quick background on Margaret. She is a recovering physicist. She studied physics at the University of Queensland and the University of Sydney. She's Australian. She grew up in Queensland, so she comes by her love of coral reefs honestly. The Great Barrier Reef being right on the border, the edge of Queensland. She herself went from the physicist training to becoming a science writer. 3 major books. The first, Pythagoras' Trousers, which is summed up by its subtitle, God, Physics, and the Gender Wars. Very interesting book about, partly about why there were so few women physicists, and having to go back the origins of physics in religion and so forth, which very interesting book. Then she wrote a book called The Pearly Gates of Cyberspace, which was a history of concepts of space from Dante to the internet, and in ways that you'll see in a minute, that mathematics, oddly enough, brought her to the coral reef. Her most recent book, just out, is Physics on the Fringe, about outsider physics, and particularly interesting character named Jim Carter, about what goes on when people outside the academy develop unifying theories of everything and how to evaluate them. In this context, the fascinating thing about Margaret is that she's a twin. Her twin sister is an artist, or recovering artist, I guess, who is an art professor and a writing professor at Cal Arts. And the two of them together founded an institution in Los Angeles, a wonderful institution that's been going on for many years, called the Institute for Figuring, as in figures as numbers, figures as drawing. It's basically about the intersection of aesthetics and science. And it's been a terrific thing. Until recently, it didn't have a home. It just now is getting a home, but it was having exhibits all over the place and lectures. It was the sort of thing where you could go to lectures on the physics of snowflakes, the invention of kindergarten, how flies fly, a wonderful exhibit they put together on an outsider logician, a logician who doesn't have a PhD but has figured it all out, alternate theories of perspective, why things fall down, the mathematics behind cat's cradles and paper folding, quantum pseudo-mysticism, all kinds of great subjects. And in the context of all this, well, I'm going to let her tell you the story of what happened, but I think you're, after this, going to both want to follow more on the coral reef, but more on the Institute for Figuring itself. So without further ado, here is Margaret Wertheim.
Thank you very much for inviting me to Abu Dhabi. It's always been a dream of mine to come to the Middle East, and I'm thrilled by the prospect that there might be some crochet coralling going on here. I want to begin today by just giving you a very, very brief introduction to the general context in which the crochet coral reef takes place. It's part of, as Ren said, an organization that my sister Christine and I founded called the Institute for Figuring. And we have a general ethos that what we're trying to do is to engage people with the subjects of science, mathematics, and engineering by really looking at the poetic and aesthetic resources that are present within these fields. So what the Institute for Figuring does is we don't actually generally get artists and scientists together. We actually look at areas of science and mathematics and specifically say, can we bring to the fore of consciousness the beauty and the creativity and the wonderfulness of these things as basically aesthetically enchanted domains. So what does the Institute for Figuring do? Well, our mission really is to creatively engage with these fields by a series of or a series of events, including we do exhibitions like the Crochet Reef, we do workshops, lectures, we publish small books, and we have a very extensive website, if any of you are interested, at theiff.org. Increasingly, what we're doing is participatory programming, like the Crochet Reef project, that engages whole communities, both locally and now increasingly internationally. And what we're interested in doing is presenting to people their notion that they can engage with scientific and mathematical and engineering ideas by literally doing things, making things for themselves. So a whole part of our ethos is that most people are used to thinking about science and mathematics as things that you have to learn by reading textbooks and writing down equations. And those are very, very valid forms of pedagogy. That's what I learned when I spent 6 years at university studying science and math. But our belief is that there are other ways of engaging with science and mathematics that are embodied, physical, that involve making and doing, that really anybody who's interested can be a part of. As Ren said, we are about to open our own exhibition space in Los Angeles. We've been operating since 2003, so the Institute for Figuring has been in existence for 8 years. But all of the programming and exhibitions that we've done so far have been done in other institutions, places like the Hayward Gallery in London, the Smithsonian in Washington, D.C., and a whole series of venues across America and increasingly in Europe as well. So one way we think about the Institute for Figuring and the general conception of what we're trying to do is that the Institute for Figuring is a play tank. So you know how in our society now we have these think tanks where great minds come to think fantastic ideas, and they generally tend to write books and opinion pieces as a result of their activities. Well, Christine and I both believe that we also need to have play tanks in our society, places where people can literally come to play with ideas. And that's what we think that the Institute for Figuring is a home for doing. So the project that we have done, which is way and above the biggest project that we have ever engaged in, is based on this Hyperbolic Crochet Coral Reef project. And this, the title that you're seeing up there, Hyperbolic Reefs, Rubbish and Reason, was the title of the most recent large exhibition we had of the project, which was held at the Williamson Gallery and Art Center College of Design in Los Angeles. And I hope by the end of this talk that you'll see that reefs, rubbish and reason are three concepts that come together in this beautiful way in the project. So let me begin to discuss the project itself by just showing you a few pictures of what it looks like. It's here on the left, you see a giant orange coral pile, and you see the human hand. So you get some sense of the scale of these works, but it gets a lot more. So here's a photo from a show that we did at the Smithsonian last year. This exhibition was held in the Smithsonian's National Museum of Natural History in Washington, D.C., and it was first and I believe the only time that the Smithsonian Institution has done a community art-based project. Ultimately, in this project, almost 1,000 people from the Washington, D.C. area and ultimately all over America participated in the creation of making a Smithsonian community reef that was shown alongside the works that we produce at the Institute for Figuring. We've had exhibitions of the project in many, many different places, including the Williamson Gallery in Los Angeles, the Hayward in London. We've done them in Arizona, New York, Chicago. Ren brought us to the Chicago Institute of the Humanities, which was one of our earliest shows. And what you get to see from some of these photographs is that the Crochet Reef project has evolved so that there are now, as it were, a whole ecology of reefs. here's a picture from the Williamson Gallery where you see that there's half a dozen different cases of the works, and in each one it has its own aesthetic. So these ones are all white, which are indicating the coral bleaching. These are our bleach reefs. And then you see at the back there's ones that are more multicolored, and I'll show you some more close-ups of those. But this is to say that basically the crochet reef, we call it the crochet reef, but actually there is now many crochet reefs. And they each, we've tried as we've gone along to sort of, as it were, let them evolve so that there is a sort of inner organicism to this project, that it all starts from very simple seeds, very simple forms, which are based on mathematical structure that we'll talk about in a moment, but that the project has sort of developed, as it were, its own evolutionary potential, so that it's now really got to the point where there is a whole taxonomy of crochet reefs and crochet reef species, as it were. These works that you see here, we call this our giant coral forest, and this was a new installation of the project that we put together for the recent exhibition at Art Centre. And just to give you some sense of scale, this guy here, he's on his pedestal, but you know, with the pedestal on the top of him, that's about 10 feet high. And each of these pieces involves hundreds and hundreds of individual crochet pieces. So each one of these works is in itself a whole little ecology, which of course is what an actual living coral reef is. Coral reefs are made up of hundreds, if not thousands, of individual coral heads, each of which itself is made up of thousands and thousands of individual coral polyps. So each bit of reef is itself a whole collective ecology of individuals and species. And this is essentially what we're trying to mirror in the installations that we do. As much as possible, we try to mirror and, as it were, not just in the visuality, but in the process of making, this project actually mirrors the way that a lot of coral reefs actually work in nature. This was one of the installations from the Hayward Gallery, and here's what it looked like at the Chicago Cultural Center in 2009. Which Ren kindly invited us to do that work then. So this was sort of our classical period when we were really trying to, we think of these as being a bit like our Dutch landscapes. So we've actually been through lots of different phases in this project. We've sort of in some ways recapitulated the history of art. We've had pop art phases and minimalist phases, and this is our postmodernist phase, which all of this that you're seeing here is actually made out of plastic, and I'll talk about the plastic part of the project in a minute. So you see something of the diversity of what you can produce making crochet coral works. So let us talk for a minute about why on earth are we trying to have a crochet invocation of a coral reef? Well, the project really stems from being a response to the dreadful plight that is facing coral reefs all over the world, which is precisely what the conference here in Abu Dhabi is trying to address. Coral reefs all over the world are being devastated by many, many stresses at the moment. The traditional ones of overfishing, pollution, toxic waste dumping at sea, runoff from sewage. But in the past 10 years or so, scientists have understood that coral reefs are also facing two brand new stresses, which are really, really key. And that is the twin stresses of global warming and ocean acidification that are caused by the CO2 that we're pumping into our atmosphere. The Great Barrier Reef, which is in the state of Queensland, where Christine and I grew up, is sometimes considered to be the world's largest living organism. It's 133,000 square miles, and already a third of it has suffered from coral die-off. The temperature in the Barrier Reef now is around 1 degree warmer than it was a century ago, and it's estimated that it will be, by the end of this century, at least 3 degrees warmer, perhaps a lot more. Nobody knows if the reefs, if the Great Barrier Reef, the coral organisms, can actually withstand such a rise in sea temperature. Maybe they can, but maybe they can't. It's entirely possible, some scientists believe, that by the middle of this century, that reefs will stop growing. The biggest problem that they face, even more than global warming, is the fact that about a third of the CO2 that comes from that we pump into the atmosphere ultimately gets absorbed by the oceans, which first sounds like a good thing because you're taking the CO2 out of the atmosphere. But the problem is that when it gets absorbed by the oceans, it makes the oceans acidic. It changes the basic chemistry of the seawater, and that actually prevents the coral reef organisms, the little polyps, from forming the bony structures that make the beautiful structures that we all associate with reefs. Scientists are now actually talking about the Coca-Cola ocean. This affects not just coral reef organisms, by the way, but all shell-building creatures. The increasing acidification of the ocean makes it impossible for all marine organisms that form these bony shell structures to actually make those structures. Now, you could say, why does any of this matter? What would it matter if coral reefs died out? Well, apart from the great loss aesthetically to planet Earth, coral reefs are estimated to be home to several million species. Those ecosystems might potentially face catastrophic collapse if the coral polyps are no longer able to continue building the reef structures. Now, given that we decided, Christine and I, in about 2005, that we wanted to make an invocation of a coral reef to try to bring some attention to the plight of coral reefs. And we decided that we wanted to do it as a collective art project. But why did we decide to do it in wool? Wool and water don't really go together. Why not, if you want to make an artistic invocation of a coral reef, why not paint one or carve it out of wood, chisel it out of marble? Why do it in crochet? Well, it turns out that this is not an arbitrary aesthetic choice. It's actually a logical necessity that if you're going to do it, this is the way you ought to be doing it with crochet. And that is because these frilly crenellated structures that you see here realized in crochet are actually models of a kind of geometry called hyperbolic space, hyperbolic geometry, which is what is naturally realized in coral reef organisms. So here are some photographs of a number of coral species, and you see these frilly crenellated surfaces. And throughout reefs, we see these structures realized, and they're all biological manifestations of this hyperbolic geometry. It's realized in the shapes of corals and sponges and kelps and sea slugs and nudibranchs. There is, as it were, in the marine world, a natural taxonomy of hyperbolic wonders, and we'll get to a little bit later why nature wants to realize these structures so much. But they are endemic throughout the coral reef ecosystems, and there's very good reasons for it. And it turns out, although nature has been doing these structures since the Silurian age, human beings only discovered hyperbolic geometry in the 19th century. And it was a huge shock to mathematicians to discover that this geometry was possible. It was an alternative to the two kinds of geometries that mathematicians already knew about, which we'll discuss in a second. But when mathematicians discovered hyperbolic geometry in the 19th century, they didn't know how to make models of it. They had the concepts in their brains. They could write equations about hyperbolic geometry, but they didn't know how to make models of it. And they hadn't yet recognized that it was endemic throughout the marine world and also in a lot of terrestrial plants, including lettuces. So the mathematicians struggled with, what does this hyperbolic geometry look like? How can we make representations of it? And it wasn't actually, astonishingly, until 1997 that any human being knew how to really make models of this in themselves. And that was a discovery that was made by Dr. Dana Taimina, a mathematician at Cornell University who had grown up in Latvia doing feminine handicrafts. And when she found out about hyperbolic geometry in 1997, it suddenly occurred to her that she could make models of this using knitting and crochet. And the first one that she made was knitted, but she ultimately realized that crochet was a better way to go. But what was amazing about this discovery is that it took a feminine handicrafter to realise that you could actually make models of this abstract mathematical form that you could literally hold in your hands. So let us just spend a minute or two talking about the mathematics here. What is this extraordinary hyperbolic geometry that mathematicians struggle to understand for so long, but which sea slugs and nudibranchs and corals had been doing for hundreds of millions of years? Hyperbolic geometry or hyperbolic space is an alternative to the two kinds of geometries that you all know very well. And you actually know a lot more geometry than you probably think you do. So at school, we all learn about Euclidean geometry, which is the geometry of a flat plane. But we all know about another kind of geometry that we're actually very familiar with, which is the geometry on the surface of a sphere. Think about the surface of the Earth, or specifically think about just a beach ball, because I want you to imagine just the surface. So basically, we have spherical geometry, the geometry of a flat plane, Euclidean geometry, the geometry of a flat plane, spherical geometry, and it turns out that there is this third kind of geometry, hyperbolic geometry, which can be understood as the geometric opposite of the sphere. So one thing that mathematicians, when they discovered hyperbolic geometry in the 19th century, what they realised is that they had discovered the geometric equivalent of the negative numbers. Now, don't worry if you're feeling a bit bamboozled here, because I want you to have that experience. I want you to understand. I want you to go through something like what mathematicians went through themselves, which is to be amazed, but not quite sure where we're standing here. So basically, mathematicians realized in the early 19th century that we could conceive of flat space or Euclidean space as having zero curvature. Spherical space has positive curvature. So it makes sense, doesn't it, that there would be something that has negative curvature, and that is what hyperbolic space is. As I said earlier, it's the geometric equivalent of the negative numbers. So you have zero in numbers, you have zero, then you have positive numbers, and you have negative numbers. And here we have the geometric parallel of that situation. But what does it mean? This is a very nice statement. It sort of makes logical sense. But what does it mean to have a negative curvature space? There are numbers of ways of describing this, but the easiest way to understand it is by looking at how you can fill each of these surfaces with little shapes. Now, on a flat plane, you can fill the plane with hexagons. And you all know this structure from a beehive. If you get little hexagons together, that's what bees do, and you fill the surface with hexagons. Now, if you try to do the same thing on a spherical surface, what you have to do is to fill the surface of a sphere. You have to basically replace some of the hexagons, which are six-sided figures, with a five-sided figure, which is a pentagon. And this is what a soccer ball is. This is also the structures of geodesic spheres that Buckminster Fuller made so famous. So what we're doing here, by moving from the flat plane, which was all hexagons, which are six-sided, to the spherical space, is we're literally taking away some of the space. By replacing some of the six-sided ones with five-sided ones, we're literally taking away some of the space, which pulls the space in on itself and makes it from zero curvature to positive curvature. So does anyone want to guess what we would do to make the opposite of this, a negative curvature space? Sorry? Yes, very good. See, you all know a lot. Basically, we replace some of the six-sided ones with seven-sided ones, which are heptagons. And what that does is it literally adds more space and makes, instead of pulling the space in on itself, it moves away for itself. So one way of understanding hyperbolic space is that it's space that continually curves away for itself. So you can do it with these tessellations. You can actually make paper models of this, but they're very difficult to make, they're hard to create, and they're also fiddly to work with. A much, much easier way to do this is with crochet. And the simple innovation with crochet is that instead of adding more sides to the hexagons, what we do is we increase the number of stitches. So the simple, as it were, insight that Dr. Diana Taimina had in 1997 was that to crochet models of hyperbolic space, what you would do is you'd simply start off with a simple line of crochet, and then as you went backwards and forward, you would increase the number of stitches at a regular rate. And by doing that, you literally add more space in and get these frilly crenellated surfaces. Now, it turns out that what you can do with these, and we can go into the geometry a bit more in the question time if people would like, but you can stitch mathematical theorems onto the surfaces. And here is proof, stitched onto this crochet model, that the most famous proposition in mathematics, Euclid's parallel postulate, is wrong. For 2,000 years, mathematicians tried to prove this thing called the parallel postulate. And after 2,000 years of trying to prove that it had to be true, what they were forced into the realization is that it actually isn't true, and that is what leads you to the discovery of hyperbolic space. But this was the first time that they could actually hold in their hands the proof of this. So if people want to have a look at that, actually I've got, this is actually a different mathematical proof, but this is the mathematical, this is stitched onto this one, is looking at what happens with orthogonal lines. So these lines are at right angles to one another, and you can see that actually, although they start off being, these two lines are parallel, they start off being at a certain distance together and then they diverge. And that's one of the features of hyperbolic geometry, is that parallel lines diverge, which again is pretty hard to understand theoretically when you learn it at university, but on these models you can see it directly for yourself. So Dr. Taimina's creation of hyperbolic crochet didn't actually introduce any new mathematics. What it created was a beautiful pedagogical revolution, and it showed us for the first time how you could visualize these structures. And it makes it Dr. Taimina and her husband, David Henderson, who teach geometry, non-Euclidean geometry at Cornell, use these models to introduce students to what would otherwise be extremely abstract concepts that are really quite hard to grasp when you study them purely through theorems. But as I said, human beings struggled to understand this. But once you've got the models in your hands, you can start to see very easily how you can, as it were, play with the structures. So if you take a very mathematically pure one, like these ones, this is a good one. What you see, this is a mathematically perfect one, but it has a very sort of clear sort of mathematical perfection to it. And as long as you keep making the mathematically perfect ones, they have this great elegance, but they don't look particularly natural. And the reason that we started the crochet, or how the Crochet Reef project came about, was that my sister Christine, after making the mathematical models, the pure ones for a while, came home one day and said, you know what, I'm sick of making pure mathematics. I want to branch out. I want to see what happens if we be a bit deviant. What if we don't stick to the strict formula? What if we actually go a bit wonky? And me being the scientist, I said, oh, no, we have to stick to the formula. But there's only so much you can actually do with the strict mathematics. And of course, nature doesn't feel compelled to stick to strict mathematics. There's lots of things in nature that are almost spherical, but there's nothing in, like eggs or sea urchins, there's nothing in nature that's pure mathematics, that's purely spherical. It wouldn't look natural if it was. And the same is true with hyperbolic structures. There's nothing in nature that's a pure hyperbolic structure. They're all a bit deviant and aberrant. And so Christine decided she wanted to start making deviations in the code, as it were. And as soon as she did that, the structures started to look natural. And after about a week of this, where Chrissy would be making wonky ones, and I was still there making purely mathematical ones, her wonky ones were sitting on our coffee table, and we looked at them and we thought, oh my gosh, they look like a coral reef. And Chrissy uttered the phrase, we could crochet a coral reef. And she likes to remind me that she used the conditional tense. We could crochet a coral reef. So we had a few of them sitting on our coffee table, and we thought we could crochet a coral reef. And we conceived of the idea that it would be nice to have some women do it with us. So I put up an announcement on the Institute for Figuring's website asking would there be anyone else who might like to join us in crocheting a coral reef in this sort of mixture of mathematics and handicrafts and environmentalism. And 3 weeks later, the Andy Warhol Museum rang and said, we're having an exhibition on artists' response to global warming. We'd like you to have we'd like to have your coral reef in it. And I laughed and said, well, we've only just started. It's going to take a fair while, but you can have a bit of it. So for the Andy Warhol show, we made a couple of small installations, and you can see pictures of them here, and people really liked it. And then Ren Weschler invited us to fill a 3,000 square foot gallery in the Chicago Humanities Festival, because their theme in that year, in 2007, was global warming. Now, a 3,000 square foot gallery is a huge space to fill. And I have to say that I said yes to this proposition only because at that point I had never put on an exhibition before. I was a science writer. I knew nothing about filling a 3,000 square foot gallery with material objects. So I came home and I put this proposition to Christine, and she said, you're absolutely mad, we can't do that. That's an enormous exhibition. But to her credit, instead of being daunted by this prospect, she went into crochet overdrive. And Christine has single-handedly produced about as much work as everybody else put together. And here you see some of the work. And to give you some idea of scale, this was arranged in like a ring-shaped atoll that was about 20 feet in diameter. And those pieces on the wall, they're each coral mounds that are about that big. Again, each one covered in hundreds of different models. And after Chicago, we got invited to do it in many different places, New York, London, etc., etc. Most recently at the Smithsonian in Washington, D.C. But a beautiful thing happened on the way to doing this. The first time we had the big exhibition in Chicago, we decided together with Ren and the Chicago Cultural Center that it would be nice to have the local people participate. And it would be nice to have, along with the reefs that were coming into being through the Institute for Figuring and the few dozen people that we were working with, that it would be nice to have the local people do a Chicago reef. And so they did. And over the course of 6 months, I think about 200 or 300 women in Chicago participated in building a Chicago reef. And then we did a community reef in New York and Arizona and very many other places. And here is an installation of, this is the Chicago reef and the New York reef combined together into a single thing. And this is just part of the structure. So you get some sense of the scale of how big this can become. Here is Chicago and New York, and this top one on the left-hand side is Arizona. This was an exhibit that we had in Scottsdale, Arizona. And since then, we've done these community reefs. We've worked with local communities in Chicago, New York, Arizona, London, Ireland, and Washington, D.C. They're all the places that we've had the big exhibitions and worked directly with local communities. But a very lovely and unexpected thing has begun to happen. The project has gone viral. And what's happened now is, just as living reefs send out spawn that fall down and start to form new reefs elsewhere, so the crochet reef has sent out spawn. And now there have been communities all over the world, in Sydney, Melbourne and Perth, Adelaide in Australia, all across the USA, including many states. More recent ones is Indiana, Florida, Maine, are making crochet reefs. And we've had them in Croatia, all over Latvia, and now there's one going on in South Africa. The biggest reef that we've had so far that has been done is the one that was done in the Smithsonian, which was called the Smithsonian Community Reef. And it was this incredibly beautiful, ultimately mountainous structure that over 900 people contributed to. And just to give you a sense of scale, this was on a platform that was 10 foot wide by 16 foot long, and it went up to about 9 feet high, and it was completely packed like this sort of Mount Everest of reefs through the work of almost 1,000 women. A very special reef has been the Latvian reef, which was organised in 2008 and 2009 by Ms. Tia Viksner, who is a crafter in Riga. And I love this photo because it's, this is basically, to me, so sort of still Soviet. But in what you see is this is Tia's crochet group in Latvia, and all of them are wearing handicraft dresses that they have knitted and crocheted themselves. So in these countries, the handicraft traditions are so alive and vibrant, and the work that they produced is amazing. We've had, I just want to show you some of the people. This work is quintessentially done by human beings. An extraordinary range of human beings have participated in the project. On the left, we have two of the young women from the UK reef that we did in conjunction with the Haywood. And here on the right are some of the women who participated in the Indiana reef, where they went and worked with women in the Indiana State Prison who produced a little prisoner's reef, which was just incredibly moving. The project also involves remarkable individuals who have worked directly with Chrissy and I at the IFF. This woman, Kathleen Greco, has been one of our very special contributors. She is a former industrial designer who designed this vinyl thread called jelly yarn, which specifically she made it to crochet with, or to knit and crochet with. There wasn't a vinyl thread on the market that was good to crochet with. And she, Kathleen, set out to design one, and she now has a little company that sells it. But here she's making a piece of jelly yarn sand for us. It's like a sort of a mat that we put some of the corals on. And the reason that she's actually putting it in the oven is not arbitrary, because actually when you make a big piece of this, it's quite stiff, and if you gently bake it in the oven, it softens the vinyl and makes it sort of more pliable and fabric-like. This is just one of the other remarkable contributors we've had to the project, Helen Bernasconi, who's a former computer programmer in Australia, who left being a computer programmer to have a little sheep farm in a place called Bonnie-Doon, which is in the middle of nowhere. And she grows the sheep, shears the sheep, spins the yarn, dyes the yarn, and makes it into these extraordinary things. This is what we call our hyperbolic sea snake. It hangs about 30 feet high, and it's based on, it's a crochet hyperbolic invocation of the rainbow serpent, which is the premier mythological spirit of the Aboriginal Dreamtime. So what we've discovered through this project is that there is indeed an entire parallel universe of creative feminine energy waiting to be tapped. And everybody who comes to this project who applies themselves starts with the simplest of these crochet structures, the simple mathematically pure ones, which are extremely easy to learn to do. But what has happened is that as people have started playing and experimenting and deviating, they have produced, as it were, a crochet tree of life. So there's this huge taxonomy of forms that can be brought into being. And it is really equivalent to the tree of life on Earth. Just as all life on Earth starts from single, simple-celled organisms and gradually diversifies and complexifies as the DNA code gets more and more complex, so too that has happened with the Crochet Reef project. The very simple instructions for how to make these models is simply crochet n stitches, increase 1, crochet n stitches, increase 1. But once you start playing with the code and making complexities, you get this huge taxonomy of extraordinary structure. And I just want to show you a few of the absolutely remarkable things that our most committed contributors have produced. And each one of these women, they come from all walks of life. Some of them are scientists, some of them are mathematicians, some of them are housewives, some of them this one is a costume, Ildiko is a costume designer. Evelyn Harden, who is, I think, one of our most creative geniuses, is a high school dropout from Texas who's got pregnant at 16 and left school and has never had any formal education since, but has produced a body of work of extreme aesthetic amazement. This work here is by two people. Anita Bruce has knitted this whole series of works out of scientific wire. This is wire used for electronic circuits of some kind. And then Rebecca Peoples has made a series of these little gold and red beaded ones, which she took the techniques of crochet and the exact same algorithms and transformed it into beading and made these mathematically pure, perfect little forms out of beading, but they're like little miniature Byzantine marbles in these wonderful colours of golds and reds and blues. We've actually had a number of people who've done things in beading, just simply taken the crochet instructions and transformed them into beading algorithms. But this woman, Sarah Simons from Los Angeles, has produced a whole body of these ones out of beading that look like kelps. More beading from Sue Olson. I should say all the beading ones, most of the people who do them tend to do them mathematically perfectly, but it's just the choice of materials that brings into being these extraordinary forms. And I'll end today with a brief discussion of the final element of the project, which is crocheting out of plastic. One can take plastic and make thread from it. So in this case, what we have here is Claire O'Callaghan, a school librarian in Los Angeles, has made a whole grove of blue crochet corals out of the plastic wrappers that the New York Times comes in. In America, when you get the New York Times delivered, it comes in a blue plastic wrapper. And Claire has been keeping her New York Times plastic wrappers for 30 years. And when she encountered the Crochet Reef project, she made an entire grove of crochet plastic blue creatures. And the little embellishments up the top are made from things like drinking straws and other plastic refuse. Here is Kathleen Greco, the woman who made jelly yarn. She crocheted a series of these anemone forms out of this vinyl thread and put them in snow globes. And here perhaps is our most unusual object. This is crocheted. This is the only thing in the show that has electricity running through it. It's made by a woman, Eleanor Kent, who is an electronics artist in San Francisco. She's now an 85-year-old grandmother. And what she has made these hyperbolic sea creatures out of is a material called electroluminescent wire. It's wire that's covered in a kind of plastic thread, and when the current goes through the wire, the plastic lights up. This material was actually developed by the US military for lighting the insides of tanks and for laying out military airstrips in places like Iraq. And Eleanor took this material and wanted to repurpose it for something beautiful and non-military. So she made us a series of these hyperbolic crochet corals, which I think look remarkably like fluorescent, bioluminescent sea creatures. Eleanor, as I said, is an 85-year-old grandmother now, and she calls this Granny Tech. So I just wanted to show you something of the extraordinary creativity that these women bring to the project, not just in terms of form and structure, but their thinking about what materials that they could use, how they could take something that, the first inclination is just to do it in wool, and then here we have something that is, as it were, designed for military tanks. The plastic project is particularly important to Christine and I because it responds to another crisis that marine life everywhere is facing, and that is the problem of oceanic plastic trash. Many of you, I'm sure, are aware that there is this huge environmental crisis of plastic trash going on, that the plastic that we humans create, a lot of it ends up washing into the sea through storm drains, etc., and it accumulates around the Earth in these big vortexes of floating plastic trash, the biggest one of which is northeast of Hawaii in the Pacific Ocean, and it's now referred to as the Great Pacific Garbage Patch. Here is some pictures of plastic trash collected by Greenpeace in the northeast islands of Hawaii, where this plastic, where basically those islands get inundated by this tsunami of plastic trash from the garbage patch region. Each year, humanity produces 100 million tonnes of plastic, of which it is estimated that at least 10% ends up in the sea. In the area of the Great Pacific Garbage Patch, there's now 6 kilos of plastic for every kilo of living phytoplankton. So basically there's 6 times as much plastic as there is living matter. And it's estimated that this plastic now kills 1 million seabirds every year who basically eat this plastic garbage thinking that it's food, and then they die of starvation, and it kills 100,000 marine mammals. Here is what the mouth of the Los Angeles River looks like on any given day, and most rivers in most big cities have these big berms at the mouths of them to try to stop the plastic trash from going into the sea, but we can only collect so much of it, and a huge amount of it does end up going into the sea anyway. When Christine and I heard about the Great Pacific Garbage Patch, we decided that we ought to crochet a plastic, as it were, response to this, that this would be, as it were, a plastic crochet reef that would be, in a way, the kind of satanic twin of the beauty of the classical yarn-based reefs. So we decided, I mean, it's very sort of ironic that at the same time that the beauty of living reefs is being destroyed and we're losing this vast aesthetic resource in the ocean, that into the void is coming this new thing, this plastic monstrosity that we humans are in the process of creating inadvertently. And so Chrissy and I decided that we should, as it were, we should parallel this in the project. And so we decided to crochet what we call a toxic reef out of our household refuse and other plastic materials. And so the last few years we've been crocheting a toxic reef, and here it is all made out of plastic trash. And this is one of the incarnations of it. But we decided that that wasn't good enough, that as well as having an artistic response to the plastic problem, that we ought to do something to actually change our behaviour, or at least to become aware of our behaviour. Otherwise, it was just, as Christine likes to put it, more geep gauze for social change. So what we thought we would do is we'd keep our own plastic trash and see how much we used. Now, we were raised to be ecologically aware. We don't use a lot of stuff. But nevertheless, this is how much plastic domestic trash Christine and I accumulated in a month. So this is, all of the plastic that we used at home, the shampoo bottles, the dishwashing bottles, any takeout containers, the plastic bags that we brought home from the shops. We were so horrified at the end of a month that we thought 2 things have to happen here. One is that we should keep going and see how much plastic we would accumulate over a longer period of time. And the other thing is that we have to change our ways. We ended up keeping all of our domestic plastic trash for 4 years. We live in California, we have a garage, we could store it. But we kept all of our trash for 4 years, which is incredibly tedious because it means you have to wash it and bag it and keep it. And you have to make sure that you wash it properly so it doesn't go off. And 4 years later, it was exhibited at Art Centre College of Design along with the beauty of the yarn-based reefs. So here is basically the toxic reef as it has evolved. all of the black material, by the way, is crocheted videotape. And then here on the left-hand side, we have what we call our midden. And the midden is a refuse dump. And basically, this is Chrissy and my plastic midden of 4 years' worth of our plastic garbage. And for us, this has become an extremely important part of the project, because this is something that every single human being can do something about every single day to help save marine life. Every plastic bag that we don't bring back from the shops, every bottled water that we don't use, every shampoo bottle that we don't use, all of that is one less plastic piece of rubbish that doesn't go into the sea. And we're trying to encourage, when we have community groups to do the project now, to perhaps think about using plastic and doing their own plastic midden. The midden project, as I say, is an offshoot of the Crochet Reef, but it is an integrated part of the whole project, which is really about trying to bring attention to the plight of the dreadful plight that is facing marine life all over the world. We have, for those of you who might want to know more, we have 2 extensive websites where you can access information about the project. crochetcoralreef.org, which is a dedicated site that we now have for just the Crochet Reef project, and that can also be accessed through the IFF's own website, theiff.org. So thank you very much, and please let us have some 15 minutes or so for a discussion and comments, questions, anything that you would like to discuss. Yes?
Hello, thank you so much for a nice lecture. I'm Ammar Sakaji, theoretical physicist. I want you to come back to physics. Regarding, as we know, in cosmology we have open and a closed model of cosmology. I think hyperbolic is very related to the open model of universe. Open model. Open, closed and open universe.
Open, yes.
Open. For
yes.
hyperbolic is
yes.
it's equivalent to open model. Right now,
yes.
as we know, if you want to calculate the metric, Einstein relativity, the metric ds, it's possible to calculate the metric for such shapes.
I'm sorry, what is the question?
Is it possible to calculate the metric ds for such shapes? Because it's hyperbolic geometry, and the metric, I think, can be calculated in general for simple case.
Can somebody give me there's a purple model floating around, the one that has the the theorem stitched onto it? Thank you. The man is asking a question, a very nice question, about basically the possibilities for hyperbolic space being the structure of the universe. It is an open question at the moment whether we live in a universe that has flat geometry, spherical geometry, or hyperbolic geometry. And that is one of the reasons that we're investing in things like the Hubble Space Telescope, is to try to determine what is the geometry of the universe as a whole. This is a question that basically, this is the equations of general relativity tell us the structure of the universe, but we need to have some specific data from the universe to find out which specific case we're in. Most of the evidence at the moment, and for a long time, has been that we live in a universe that on a big scale is Euclidean. But there is some very intriguing evidence that we potentially live in a hyperbolic universe. Most physicists or most astronomers think that that evidence is just an artifact of the telescopes, but there is some possibility that we live in a hyperbolic universe. Now, how would we know which universe we live in? Well, the way that we can determine it is through the behavior of parallel lines. And what is it in the universe that do you think travels in parallel lines that would enable us to determine this? Light, very good. So basically, when we look at far away objects, far away galaxies and stars, if we see that the light is always traveling in parallel lines, and those parallel lines stay the same distance apart, then we know that we live in a Euclidean universe. If we see cases where the parallel lines seem to ultimately intersect one another, like on the surface of the Earth with the lines of longitude, then we would know we live in a spherical universe. But if we see cases where the two lines that start off parallel then begin to diverge, then we would know we live in a hyperbolic universe. And that is what you see here, that we see these, we have one line there, and there are two lines that are crossing it. And these two lines, they start off a certain distance apart, and then they gradually diverge. So these are two parallel lines that are diverging. Now, if we look out in space and see that happening, then we would know that we live in a hyperbolic world. So your question, the man's question is about the metrics, which is its question about distance. How far apart are things? And yes, we can measure this. And as I say, that is one of the big questions that astronomers are trying to do right now, is measure the behavior of parallel light waves from the distance past.
What kind of universe do we live in? They've been looking at light maybe for many years now. Have they realized or discovered anything? What kind of universe are we living in?
Well, on the local scale, what astronomers have discovered is that Einstein is right, that general relativity is right, and that what general relativity says is that if you live near a heavy body like a sun, like our sun is a heavy body, and it warps the structure of space away from Euclideanness, and that as light waves come near to the sun, they will bend around it. The space is literally bent, and the light waves will be curved around it. That was a prediction that Einstein made with general relativity. And in 1919, for the first time, astronomers found evidence that that is indeed going on. So on the local level, we know that space is curved, that the geometry of space locally is all uneven and bendy and wavy. And that was an astonishing thing to discover. And it was based, Einstein's theory was based on marrying our understanding of gravity with these new geometrical ideas that had developed from the discovery of hyperbolic space. But there is a question of what's the big scale of the universe? Like if you look at the universe as a whole, is it more like a flat sheet with a few, lumps and waves in it, or is it more like the surface of a beach ball that curves back on itself, or is it like a hyperbolic plane that it's open, as this man said, and goes away from itself? And most of the evidence is that on the large scale we live in a universe that is flat, that it's Euclidean. Now I should say we have to talk about this in 4 dimensions. It's the 4-dimensional version of a Euclidean, but that's the evidence.
I have another question regarding the patterns. I mean, do you have any patterns or algorithm on your website that
Yes.
people can follow to actually crochet?
Yes, we have a lot of information on our website, and if anybody is interested in acquiring more, we published a little book about, it's called A Field Guide to Hyperbolic Space. And it is a brief introduction to the history of the mathematics, and then the second half of the book is devoted to algorithms for making the variety of structures. So you can get that on our website, and I bought a few copies to leave for the Institute.
Hi, my name is Aruba Samarai. I'm a radiation medical physicist, but my question is not related to physics. I'm very impressed about your presentation. It's a very new thing to maybe this region, and I think we are going to benefit a lot from these ideas. My question is, when you do the exhibitions or participate in any of these activities, and a lot of people participate in doing all these crochets, are they keeping them stationary exhibitions somewhere, or do you take them and redesign them in another one, or when you move from one place to another, you get some of these and then redesign them again in another exhibition? I just wonder what you do in this crochet.
Yes. Yes.
Okay.
It's a good question, and there's multi-parts to the answer. The exhibitions that we have done so far, every time we do it, it has been different. So it's very labor intensive to do this work because it has to be, each time it's had to be grown in place. Now, as you saw in some of the works, there has been, some stability has been brought. Let's see if I could get, okay. Well, no, it's, sorry, I have to get, okay. Over the years, we have evolved some stability. So this one, for instance, is now set. It took a long time for it to, as it were, evolve into its final state. But all of them, there's a whole series of them that have become, as it were, stable. But mostly, each time we've done the exhibitions, it's been grown in place for the space, because the exhibition spaces we've had have been wildly different. Some huge, some very small, some with windows directly onto the street, some completely in the dark. So it's very organic and has really been done in response to the venue, which makes it extremely time-consuming. And each of the community reefs obviously has to be made in situ because it's never been done before. So one of the wonderful processes that takes place is once the people have made all of their work, you just have these huge piles of stuff just sitting around, and it really doesn't look like much, and it basically looks like an explosion in a thrift store. And it takes a huge amount of intelligent curating to make it actually look like a beautiful installation. So over the years, we've developed a series of techniques for taking all of this stuff and saying, okay, how do we make it into what A looks like a coral reef and B looks beautiful? And we work with the local people on that part of it too. Then the question, another part of your question is, well, what happens to it afterwards? What happens to the work? And that's an ongoing challenge. The work that we've produced, like these ones, some of them are now being completely stabilized and crated up so that they can just be, as it were, sent to institutions. At the moment, we're doing that with a small subsection of them. But it remains an ongoing issue, what happens to the community reefs. Because the institutions get very excited about making them and all the participation, the community engagement. But then there is the issue of what is the commitment to preserving them and keeping them. And there is no canonical answer to that. Some of them are sitting in, we have 3 of them in our storage, but some of them have been lost, or they've just been dissipated because the institution didn't have the place or didn't have the willingness to keep them. Some of them are in the institutions being stored, but it's a problem.
Well, as an Australian textile physicist who likes to dive, thank you for an intellectually stimulating talk.
Yeah.
Why do marine organisms choose hyperbolic geometry?
Oh, good, yes. So do you want to pass? This one is a very beautiful one. Okay, so why do organisms use hyperbolic geometry? Does anybody want to take a guess at this? I'm sure. Yes, and why? This man says surface area, but what is it about the surface area? Sorry?
They can draw more food and sustenance out of their water.
Yes. So this gentleman has answered the question correctly. What happens is these surfaces basically are a really good way to have maximal surface area in a given volume. And so it's a way to get a lot of surface. And so if you're a stationary creature anchored to the sea floor, and you can't go chasing after your lunch. You need your lunch to come to you, and so you're basically just filter feeding. You need to maximize surface area to maximize your intake of nutrients. And this is also why, and it's both nutrients and sunlight, and this is also why some plants, like some species of cactus and lettuce leaves, for instance, have hyperbolic structures too. It's to maximize the opportunity for photosynthesis.
Hi, I found you through Google Images because I was doing freeform knitting and I realized I sort of knitted a sea scene and I needed some coral. And this is my little example of coral that I crocheted after seeing your site. What I actually fell in love with the idea, and I thought this would be a brilliant thing to do in the Middle East, because on top of it being a sort of woman only and woman empowerment and sustainable, and we have coral reefs here, we also have the issue in the Middle East where we have lots of expat women and lots of local women, and we never meet.
Yeah.
And I would love a project that would actually bring everything together and make it work as if we're in one world. And I'm up for it. I don't know if anyone else is, but maybe we can talk afterwards. But if other people are interested in doing it, I think it would be a fantastic thing to do. And we even have, you know, in Dubai, they have this amazing aquarium, and we have an aquarium here. I mean, there's places here to exhibit it. It just takes energy.
Thank you. That's wonderful. Let Ren say a few words, because this is something we are all hoping could happen.
Indeed, and just as somebody, I've taken to thinking about this as the global warming equivalent of the AIDS quilt. and it is, one of the things that's extraordinary about it is when you do this, when we did this in Chicago, and again when we did it in New York, is how it crosses class boundaries. In Chicago, we had, you know, very rich North Shore knitting clubs of rich ladies, and we had gospel groups, and we had inner city nine-year-old classes, and then they would all come together on a regular basis. It was really quite amazing. And the way we did it was that 6 months before he came to Chicago, we had Margaret and her sister give a series of classes in different places. In Chicago, it turned out, for example, that the mavens of crocheting, there was this kind of avant-garde, trendy fashion, these two identical twin black women who they were called the double-stitch twins. And they just knew everybody, and they just got that going. And in New York, we had a Harlem gospel choir that was doing it. It was quite amazing. It was precisely what you're saying, that you bring people together who would otherwise never meet each other, and otherwise wouldn't necessarily know about global warming and so forth. So it's an incredible organizing tool and so forth. And indeed, that's one of the reasons I was hoping that we could do this. Heidi, Heidi has a yellow legal pad, and when this is over, she'll be standing over there. And if you're thinking of being part of this, sign up. Let's get everybody's name on it. And my hope is that at some point in the next half year, a year, Margaret can come back and can do a whole series of classes to get it going, and then maybe a year and a half, 2 years from now, we could have a major bringing together. So again, sign up with Heidi as you leave.
And this would be absolutely wonderful to have a Middle Eastern reef. And it's interesting, I just want to make a comment about one thing that you said, which is we don't actually see the project as being for women only. When Christy and I started the project, we always imagined that the majority of whatever group of people did it would be women. But we didn't expect that it would be almost so exclusively women. We have had a few men. Of the 5,000 people that we definitively know have actually been directly involved in creating the various reefs. We know that we've had at least a dozen men. So it's not exclusively women, but it has really surprised us that 99.99% of the participants have been women. And it's interesting that the gender stereotype still very much applies in this realm of handicraft. And I don't think that's necessarily a good or a bad thing. It's just what is. It's just surprising. So we always say to people, you know, it's okay whatever gender comes. So whoever comes, it's great.
Good evening. You've talked about community engagement with reference to knitting and crochet and making the models. But what about beyond that, with engagement with the community or education in the community about global warming and plastics and recycling and etc.? Could you talk a little bit about what's happened with that connected with the projects?
Well, when we do the workshops and work with the community groups, we always begin, we give public lectures like the one that I've just given, and the workshops, we always talk about these issues in the workshops as well. So it's very much our desire that the project is there to bring women together and to do something. But that actually was very secondary. I mean, the impulse to do the project was twofold. Initially, it was to help people to understand about the mathematics. So we were doing this even before Chrissy invented the reef. But as soon as we started the reef itself, it was conceived as a way to engage people about environmental issues. And it was, as it were, only after it got going that we realised what a powerful tool it was, for the reason this woman is saying here, to literally bring women from all walks of life together. So it began, and it began primarily as an environmental awareness raising project. And then, as it were, its feminist dimensions asserted themselves with great power. And that's probably not coincidental, because Chrissy and I consider ourselves feminists with every fibres of our being, and we were raised by a feminist mother who went from being a Catholic mother of 6 to one of Australia's leading feminists and helped set up some of Australia's first shelters for battered women. But it's interesting, and that aspect of the project has perhaps come to the fore a great deal more than was consciously planned. But it does remain an environmental awareness raising program. And we do that absolutely to the extent that we can. I should say that all of the big institutions that have done it with us are very, very eager that it be used in the context of environmental awareness raising. So we discuss plastics in the workshops. The texts, when the shows are exhibited, there are texts about all of these issues on the walls.
I'm actually an archaeologist, so I'm interested in the history of crocheting. We do actually, in this part of the world, I live and work in this area of Arabia, and we find bone points and also kind of small tools made from shell that could have been used for crocheting, whatever. But actually, just in defense of men crocheting, the archaeologists usually interpret these tools as being for manufacture of fishing nets, which of course is also a kind of form of kind of crocheting anyway, using fibers of different kinds. And if you visit, for example, the Sharjah Maritime Museum, I was just there the other day, there's a sort of mannequin of a man repairing nets, and this is usually a male job, usually done by males in Arabia, and that's another idea for having a kind of crocheting project that pulls in your male side of the sort of world in Arabia, because this technique, and it's a technique which is being lost now amongst young Emiratis. They don't know how to repair fishing nets, and they do a lot of fishing with fish traps nowadays, but originally nets was much more prevalent, and I would like to see more male kind of crocheting, be it through training kids in how to make traditional fish nets. There are other ways of doing that, but don't forget that some men do like knitting and crocheting. I remember my grandmother and mother taught me how to knit, and when I was young I used to quite enjoy knitting, so it is a sort of therapeutic kind of exercise for men as well as women.
Yes, well, I mean, the fishing net aspect, would be marvelous to get young Emirati men involved with that. We have always thought the project is completely open to men as well as women, and it's just simply been surprising to us that fewer men have not participated, and it's certainly not been any conscious thing on our part to not have men. It's just they haven't. With, as I said, a few notable exceptions. But of course, in the history of humanity, these activities, I'm certain, would have been done by men as well as women. And there's actually a very lovely tradition of English and Danish sea captains who make extremely elaborate pieces of knitting and tatting on long sea voyages. And they're so there is proof that men can do extremely complicated knitting and tatting and crocheting.
Yeah, hi. I'm not sure as a coral ecologist, I necessarily agree that it's beneficial for a coral to maintain this shape in terms of maximising the surface area. And I'm thinking that it might actually be attributable to the way that they grow in some corals, where it's actually the ratio of the circumference to the surface area which limits the growth rate. And I wonder if you know what the mathematical relationship is there, whether the circumference scales with the surface area exactly in this particular shape?
Yes, I can explain that question. But lots and lots of, I mean, it's interesting that you're disputing the thing about the surface area, because lots and lots of coral biologists have said that to me. I mean, that seems to be the general view among coral reef scientists. But yes, I can talk about your specific question. Can somebody pass me back? There's a red model with a sort of circular one. Thank you. Okay. I wish I had a blackboard to draw on, but the man's asking a question about, do we know the relationship between circumference and surface area with these things? And the answer is yes, that can be calculated. Basically, does anyone have a piece of paper and a pen, and a texter? It would be very helpful just to... Thank you. Well, I don't know how much you can see, but if I draw a circle, can you all see that circle? Let's do another circle, a smaller circle. When on a flat piece of paper, there is a very simple relationship between the radius of the circle and the diameter. And the circumference. So if this is the radius, then the circumference of the circle is given by the simple rule that we all learn in school, that circumference is equal to 2 by pi by the radius, which is a very simple relationship. But on a hyperbolic surface, it's more than that. On a hyperbolic surface, because the circumference is always increasing at a faster rate, it's more than 2 pi r. So if you see this model here, you can sort of see in the center part that it's approximately 2 pi r. But in fact, out here, the circumference is a lot more than 2 pi r. So it's increasing at a lot faster rate than it would if it was on a regular circle. So you get not only a lot more area, but you get a lot more circumference. And the exact relationships of these things are, well known to geometers. So that's another way you could actually tell whether you lived in a hyperbolic space, by the way, is you could see what the circumference of a circle was. And if it was more than 2 pi r, you would know that you lived on something that was a hyperbolic surface. It's another reason why we actually do believe that we live, for the most part, in a Euclidean universe, because we do see 2 pi r holding. So you can easily calculate these things, yes. But the notion that you get more surface area which allows you to filter feed, that seems to be fairly undisputed. So could you explain what was that your idea is?
Generally what happens is with a lot of corals, if you get too much undulation in the surface, you get too much self-shading, so it's actually counter-beneficial.
Yes.
But there are a lot of corals where they actually have an excess of energy which they can't actually put into growth because all their growth is at that circumference. So if you're telling me that this circumference is scaling at a greater rate with the surface area, then that would explain why they're doing it. They're maximising their growth rate that way.
Right, okay. See, I mean, I'd like to make a point about this. Isn't it fascinating that it's like, in some sense, the corals know. And this is one of the things that really fascinates me about this, is that human beings, human mathematicians, spend hundreds of years, first of all, trying to prove that hyperbolic space was impossible, then being forced to realise that it was mathematically necessary. They couldn't understand its particular properties. And yet here are the corals, brainless creatures, just effortlessly embodying the mathematics. And I think it's a really beautiful thing that in some sense these brainless beings know the mathematics in the very fibre of their being. And so sometimes they say with this subject that the aim of our project is to get everybody up to the level of a sea slug, that we could all, as it were, know and understand hyperbolic space as much as sea slugs and corals do.
Basically, we have to begin to come to an end. I was just going to ask one quick question as a final question is you talk about why don't coral reefs look like a explosion in a thrift shop? Is there a sense in which when you're putting things together that you begin to have a sense of why coral reefs put themselves together in the ways that they do? Or
Yes, that's a good question, Ren, and I've thought about that. Let me get it. Okay. Yes, I think it's because this is my theory. I'm not a coral reef biologist, but when we curate it, so what we've done there, for instance, is like make a big mound of red with some inflections of pink, and then around it is, some sort of browny, yellowy tinged stuff, and here's a pile which is green with a bit of, or greenish things. And when you see nature, that's kind of what they do. Here's a pile of purple stuff, and next to it is some, browny stuff, and there's some yellowy stuff over there. And it's, nature seems to sort of, as it were, it's not just all mixed up, because then it would just look like brown paint, which is actually a problem that Darwin realised vis-a-vis the evolution of what we now call genes. How do you get differentiation? If everything was just being mushed together, it would just look completely murky. And the reason you don't get murkiness is because you've got a whole lot of red stuff here, and basically that's a group of organisms that are either genetically the same or genetically related. So they're all being this one. And then over here we have another group of organisms being with slightly different genes, reflecting slightly different structures, slightly different colours. And so the process of curating has really been learning how to mimic nature, and the lesson that I've learned from it is that creatures cluster together, but they don't cluster together in absolute perfection. You have to mix it in. So here's a pile of something, and it's got little inflections of algae or whatever, or other species living on it. And I mean, I've now come to have an enormous respect for nature's aesthetic genius.
we're having for those of you who'll be back in New York at NYU on February 25th, we're having an all-day wonder cabinet called Where Does Nature Get Off Being So Damn Beautiful? And dealing with aesthetics and evolution and the problem of surplus beauty in evolution. Anyway, so Heidi, raise your hand again. Or actually, go over there in the corner and see that little yellow pad? we really want to bring this to, and that involves several things. We need people who want to take part in it. We need people who have ideas about getting other people to help us take part. We need to raise some funds to be able to do it. But anyway, anybody who has ideas, sign up with Heidi. Margaret, you'll be standing out here for a little bit. Return the corals, please.
Oh, yes, if you could bring them back, that would be great.
And you get a bonus that she'll be around here talking to you a little bit about for a few minutes. But thank you so much for coming, and thank you, Margaret.
Thank you.